So hello everybody and welcome back to the Cardiff Analysis Seminar. Today it's a pleasure to have Bernardo Gonzalez Merino from University of Murcia, and he will be talking about central diagonal sections of the N-cube. Over to you.
Thank you very much, and first of all, thanks for inviting me to give this talk in this seminar in Cardiff. Unfortunately, I can't visit you because of the circumstances, but I'd love to do so. As the title says, I'll talk about some properties of sections of the N-cube. This is, let me remind, this is a joint work together with Ferenc Barza and Ferenc Fodor. I think I didn't see him so far, so he's not yet connected, and maybe he can make it. And they are both from the University of Szeged. So let me start mentioning, this will be the main object of study. We will consider the unit cube, which will be denoted by capital C to the N, center at the origin. And we will study some properties. I will explain some properties of it in terms of sections by hyperplanes passing through the origin. This was studied quite a bit ago, and for explaining in detail some of its properties, let me introduce some brief notation. Not much, actually, it's very simple, the notation this time. So for every unit vector A, we will denote by f of A the volume of the n-1 dimensional volume of the section of the cube with the orthogonal hyperplane to A passing through the origin. Then the first properties one may ask about such sections can be explained by using some nice formula, and this will be crucial in our talk. This formula is attributed originally to Polya in 1913. It was reproven several times. It was proven by Hensley in 79, by Ball in 87. Essentially, one can prove it easily that f of A can be written or coincides with 1 over pi integral from 0 to infinity of the product of this sine of t of AI over 2t, which means sine of AI over 2t divided by AI over 2t, where A1, A2 up to AN denotes the coordinates of the vector, of the normal vector A. This formula can be proven very easily by using some basic probability and the Fourier transform and the inverse Fourier transform. Very simple. Once we have this expression, then the first property I'd like to mention is the lower bound on the volume on such volume of these sections. This was proven by Hensley in this paper of 79, showing that each of those volumes is at least 1. And moreover, this happens, the equality happens, so we have such n-1 dimensional volume equals 1 if and only if the normal vector A points in one of the canonical directions of the canonical basis. For instance, 1, 0, 0, 0, 0. In this paper, Hensley proved already an upper bound for f of A. He showed that, well, the main thing he proved was an upper bound independent of the dimension. He showed that f of A was upper bounded by 5, if I'm not wrong. And he conjectured that the best upper bound was square root 2. This was proven some years later by Keith Ball in 87. And he showed that this conjecture was correct. This was the upper bound, correct upper bound was square root 2. And he also characterized the hyperplanes for which this square root 2 is attained. And it was exactly the hyperplanes passing through the origin containing an n-2 dimensional face of the n-dimensional cube. Or said in other words, a hyperplane whose normal has all the entries 0 except of 2 entries which are plus or minus 1 over square root 2. This is regarding extreme values of those hyperplane sections. we will focus today in a different property of those sections. If instead of considering one of those sections, we consider let me say, the central section of the cube, and by central section, what I mean is if we consider the normal vector to this hyperplane will be a vector parallel to one of the diagonals of the cube. For instance, consider the vector given by the coordinates 1 over square root n in each entry. This can be written, and we will denote it by capital I of n, and can be rewritten as 2 square root n over pi integral from 0 to infinity of the sine of t divided by t to the n d of t. In dimension 3, as I'm writing here, one can see this section, this central section. It can be seen as a regular hexagon inscribed in the cube. And this is the main object of study in our talk. So several things have been studied on properties on this sequence. Let me say sequence, since the beginning of the 20th century. Let me say a couple of things about this sequence, but maybe the first one, I think I read it in a paper, I think in the paper of Hensley, I'm not totally sure, but I read something like, it would be interesting to understand the behavior of such a sequence, not just because of the application, but because of other applications to the Laplace method, so to say. But the first observation he made already is the following, and it's very obvious. If n is an odd number, or n is an odd natural number, sorry, or n is an even natural number, the behavior somehow intuitively is changing, because sine of t divided by t, when it's raised to a power to a power even, then this is having positive value all the time. But if this is to an odd power, then this can get positive or negative values all over from 0 to infinity, and thus this apparently looks like quite different depending on the parity of n. But this is not quite the case, so we will understand this a bit later. Now let me remember some of the many properties that are well known on this sequence. And the first one, I'm writing Hensley, but this is attributed already to several mathematicians. One of them is Selberg. Well, the first property is that this sequence has a limit when n tends to infinity, and it converges to square root 6 over pi. Of course, this value is between 1 and square root 2. This was already, I think, surprising Hensley, the fact that this is converging. But much more is known about this sequence. Let me say that Borwein, and Leonard in 2009, they proved the following property, very important property. The sequence IN can be written as it admits an asymptotic expansion. Let me say like that. It admits such an asymptotic expansion, an expansion of the form summation of some coefficients AI divided by n to the I for I equals 0, 1, up to infinity. Actually, the fact that it admits such an asymptotic expansion was proven earlier. And I forgot the name of the mathematician. It was proven in the 90s. Not just for this type of integral, but for many others. So basically, Borwein, Leonard proved that if the sequence IN admits such a representation of a power series, then one can attempt to compute each of the coefficients of such an expansion one by one, so to say. That was the idea in the proof of Borwein, Leonard. So they really focused on computing or torturing a little bit the sequence of integrals, so that they gave you back each of the coefficients one by one. In order to do so, they actually they had to compute several derivatives of the sequence and then computing some limit by induction. So really dramatic, so to say. They computed the first two terms, this one here and this -3/20n. And with that, let me say that they already had proven that for some large enough n, then the sequence is increasing and concave. Let me also say that because of their technique, they lack of, so to say, how to compute their, let me say, remainder term here. So they couldn't compute at all the remainder. So their technique was solely saying, you obtain these coefficients and that's it. You don't know anything else. So you know that maybe for n0 equals 1,000,000, for every n greater or equal than 1,000,000, then this is increasing and concave. But you can't really say from which moment this is increasing and concave. Then Kerman, Olhava, and Spector in 2015, they proved, they computed the third term, the one I'm writing here. And they explained how to do the next computations. But it was with massive amount of computations, believe me. So part of the aim of our talk is to understand a bit better IN and to really explain how to compute this much, much, much easier. Other properties, much recently, were proven by Knig and Koldobsky in 2019. And in a very nice paper, they showed, besides other things, they had one of these properties that if n is greater or equal 3, then the value of this sequence is bounded above by √6/pi. This was already not known. So this √6/pi is the limit of the sequence, but you can figure out that you can imagine the sequence kind of doing some I don't know, some wave, because it's depending on this property I mentioned to you on the parity of n, but no, not really. And this is upper bounded by the limit. Let me just mention that Knig and Koldobsky here also proved something very connected to what Keith Ball proved a bit earlier. So they just introduced a property on studying maximal, so the sections attaining the maximum, not in the n-1 dimensional volume, but the n-2 dimensional surface area measure. And it's a very nice problem. Actually, I think they raised the question on doing the same for the so-called Quermass integral of the section. So which sections are attaining the maximum Quermass integral? And this is not known yet, except from some cases. Then an additional property was recently proven by Iskander in 2020, and it's already accepted, I think, the paper. And he showed basically that each term of this sequence, in plus 1, is greater or equal than in, but multiplied by some coefficient slightly smaller than 1. Almost 1, when n tends to infinity, is actually tending to 1, but not exactly. So all these properties are hinting that, or they are strongly suggesting that the sequence will be quite probably an increasing sequence for almost every n. The question is, really, but how can we show it? So this is regarding more or less when n is large. When n is large, this is dealing with that case. When n is small, there is a formula, an exact formula for this sequence of values. This has been proven. It is attributed originally to Bromwich in the early 20th century, but it has been proven repeatedly by several authors. For instance, in 2012, Frank and Riedel, and you see a very, well, not nasty. It's a nice formula, but very lengthy to compute. So computationally, if n is relatively not very large, you start having troubles to compute this, because there are lots of sign changes and dramatic cancellations, so to say. And in order to compute this by computer, when n is relatively large, then this gets really slower and slower. So if you check this for the first values of n, I'm showing here you two different drawings. The first one is actually taken from the paper of Borwin-Leonard. Of course, they are showing here a continuous function. This is because they were not just studying this for n natural number, but they were studying this for n real parameter. So to say, they extended this analytically to every n greater or equal strictly greater 1, and they studied properties of such a sequence. Several of those questions which are still open. So if you have a look into the sequence, you see that from n equals 2 to 3, this is clearly decreasing. So from 2 to 3 is decreasing the value, but then already from 3 to 4 is slightly increasing. And from here on, it's, well, increasing. And here we did a drawing with Mathematica. You see that, well, we made until 110, but it's there's no need to show how many, but you see, this is the behavior. So it's concave and increasing clearly. So the question is if one can really show some explicit n0 for which from that moment on, the sequence is monotonically increasing and concave. Let me also say that there are several open questions in this area. For instance, for this very particular sequence, or this function extended to the real numbers, it is not known the exact formula for the minimum value of the function, of the sequence. You can see it is approximately around 3.3 whatever, and but there is no exact formula. Also for the inflection point, because here the function is convex, and from here on is concave, there is an inflection point at around 4.4, but this is neither known, so it's just conjecture. And this is my aim in this talk, to show this theorem, that the sequence is actually increasing for every n greater or equal 3. And in particular, I'll focus on some of the parts of the paper because there is not enough time to explain everything. But we'll focus on showing that there exists an explicit n0, so that the sequence is increasing. Some questions so far? I will start focusing now on the proof.
May I ask a quick question?
Yes, sure.
So am I right in understanding that in the asymptotic expansion for large n that you showed before, so you are saying that I of n admits a complete asymptotic expansion in n, and each of the terms can be computed? There is an algorithm for it.
Exactly. Okay. Yes. You are totally correct. That's the case, exactly. But it's by hand. It seems with the techniques, this is what I wanted to emphasize. With the techniques they used, it's really hard. So the whole paper of Borwin-Leonard is just on trying to compute the second term. This was already really technical with their techniques. And this is an improvement in our techniques, so to say.
I'm sorry, could you remind what was the red graph on the previous slide?
Yes, sorry. The red graph is just the analytic extension of the sequence we are studying, but replacing n by a real parameter p, for p is greater than 1. So it's a representation of this, but instead of for n natural number n, for a real number n greater than 1. Mm-hmm. That's it. Anyways, we just focus on the natural values, on the sequence, so to say. Okay, the idea is we will start with the following observation. So when you have a look into the sine of t divided by t, you clearly see that the values of sine of t divided by t tends to 0 very quickly when t tends to infinity. And moreover, if you take a power n with n 2 or larger, then you see that as long as n is larger and larger, then this goes to 0 really quickly, except at the point t equals 0. In other words, it is very easy to see that the main part of the integral is accumulated around the origin. Of course, this idea is not, most of the ideas I'm mentioning are not new. They are already known, but well, I will remind them just in case. So we split first our integral in two parts, the integral from 0 to a and the integral from a to infinity. Of course, our aim is to show that this is the right part is becoming zero really quickly. But how can we do that? Well, let me call the first integral I sub a of n, and the second one we upper bound it by the absolute value of the sine of t, and we upper bound that by 1. Then we integrate this, obtaining this value. Of course, this value in the right hand side, if a is a number between 0 and 1, this converges to infinity really quickly. If a is 1, this is a constant, and if a constant which tends to infinity also when n tends to infinity. And if a is larger than 1, then this is converging to 0 at exponential speed. And this is therefore what we are interested in, when a is larger than 1. Let me take a to be larger than 1 as mentioned, but also smaller than pi over 2. This will be clear why I'm doing this. This will be clear in the next couple of slides. So picking up this as a constant, and let me take exactly a particular constant. This is not important, but this is in order to make the computations afterward a bit less messy. We take e to the 1/6, which is between 1 and pi over 2. And then we can upper bound the right hand side term by 2/3 a to the minus n. This, we call it e sub 1 of n. This, we use the word e because this is considered an error. And the idea somehow in the proof is splitting the main part of the integral into different parts of different errors and the main part where the integral is concentrated. And in the end show that the errors are very small compared to the main part of the main value of the integral. That's it. That's the main idea of the proof. And this is the first error, which is, as I mentioned, an exponential error. Okay, now we go back into the main part, I sub a of n. And I observe now the following. So, the function sine of t over t basically coincides, well, its Taylor expansion is the same than the one of e to the minus t squared over 6 for every degree up to the 4th degree. So they are pretty similar. This is suggesting a change of variables. Exactly this change of variables, sine of t over t equals to e to the minus x squared over 6. And this can be written explicitly in terms of x, x of t in terms of t, and being equal to square root of minus 6 log of sine of t over t. This has very nice properties. Some of them are the following. We can extend continuously and analytically the function to the origin. And it is very simple to see that the x of 0 has to be 0. Its limit is that one. And second, if let me observe that for t equals pi over 2, this converges to infinity, to plus infinity. This is the reason why we are considering a to be strictly smaller than pi over 2. In order to have a function defined in a compact interval, and so that its image goes to a compact interval, not an unbounded interval. So this is the reason why we picked a smaller than pi over 2. Now, deriving x, it's very simple to see that this is strictly larger than 0, and therefore this is an analytic function and strictly increasing, and therefore a bijection in the interval 0a. Then we can apply the Lagrange inversion theorem in order to directly obtain that t of x is an analytic function in the interval 0x of a. I'm not mentioning here explicitly the value of x of a. That's not really an issue, but this is around 1.2 whatever, so not really big. What else? So now the idea is the following. Even though t of x cannot be written explicitly, this is the typical trick one shows in the lecture of analysis, in one of the first lectures in analysis in the university, and is that even if you don't have an explicit formula for your function, if the inverse has an explicit formula and you can compute, as here, the Taylor expansion around the origin of your function, then you can also obtain the Taylor expansion of the inverse in a very simple way by, for instance, using the formulas attributed to Fadi-Bruno, basically saying that if you have a Taylor expansion of a function up to some degree, then using those coefficients can directly give you the coefficients of the Taylor expansion of the inverse function. And so you can get easily this Taylor expansion around the origin of the inverse t of x, even though we don't have an explicit formula for t. Let me say that part of the difficulties in the technicalities in the proofs of Borwein-Leonard and Oljava, Spector, and Kerman, part of their issues are somehow splitted here in this form. Of course, in order to compute those coefficients, it's a bit of computations, but doing them directly within a computer, this is immediate, this is automatic. For these terms, it's very, very, very quick, very automatic. All right. Now, derivating t, it's possible near the origin, and let me write this derivative as these first three terms in the expansion, plus this fourth term, let me call it the remainder term of x of the sixth degree, which of course can be represented as with the following form. This is because it's the sixth term, can be written as the seventh derivative of t, and this is because this is the expression, the Taylor expansion of the derivative of t already. So the seventh derivative of t evaluated at some xi in 0x times x to the sixth divided by 6 factorial. In particular, upper bounding this gives it's upper bounded by some constant r times x to the 6 over 6 factorial, where r is a number which can be harder to compute, or more or less hard, but still is a number. We know this is an analytic function, and so this is just the maximum of the seventh derivative of t in this closed compact interval 0x of a. Now we apply the change of variables in our integral, and we first of all obtain the integral from 0 to x of a of the change of variables, which is e to the minus nx squared over 6 times the derivative of the change t prime x dx. Writing this down, we arrive in the first three terms plus the remainder. Of course, the first three terms will be the ones gathering the main part of the integral. And therefore, we split it in these two parts in order to understand, in order to compute that the second term is also, a small proportion of the big one. So very, very small compared to the main part. How can we check that? We upper bound it by the absolute value of the remainder, which can be upper bounded, as I mentioned before, by this term, capital R divided by 6 factorial times x to the 6th. Now this function inside the integral is a non-negative function. Therefore, this is upper bounded by the integral from 0 to infinity, extending the interval there. And now this is, of course, basically a central moment of the normal distribution, the sixth of sixth degree of the central moment. So this can be explicitly computed really easily. with a closed formula, which is exactly 3 to the 3 divided by n to the 3 times 5 double factorial, which double factorial is 5 times 3 times 1. The important thing here is that this is basically a constant divided by n to the 5 over 2. This is upper bounded simpler by r over 2 times 1 over n to the 5 over 2. This will be the second error term. And of course, this is much larger in proportion than the first error term. Actually, this is showing that we have to be careful with when computing the main part of the integral of the asymptotic expansion, because this is really dealing in order with those terms. Okay. Now let me say the following. We go back for a second here. So we have computed already the second error term in the last term here. Regarding the one in which the integral is accumulated, most of the integral, how to compute this is as follows. We have the integral from 0 to x of a. If, well, we extend this from 0 to infinity, then we obtain again an expression which can be explicitly computed, the same we did before, can be explicitly computed as central moments of the normal distribution, different central moments, of degree 0, of degree 2, and of degree 4. And then it will appear a remainder term, which will be the integral from x of a to infinity. And this will be another error term, which we have to compute later on. So regarding the main part of the integral, it's very simple to compute that this equals this formula, these first three terms. Of course, if now you wonder if this coincides with the asymptotic expansion of that they showed at the beginning, you are totally right. This is the same asymptotic expansion. And you see how simple it was proven with this technique, with this method, the Taylor expansion, the asymptotic expansion. And this is one of the aims of the talk, to show how simple this can be proven and computed. But we have to care about the other error term, and this is the integral from x of a to infinity. To do so, let me remember that the complementary error function, which is 2 over square root pi times the integral from x to infinity of e to the minus s squared ds. This can be upper bounded by e to the minus x squared for every x, non-negative. Then if we concentrate on this integral from x of a to infinity, we aim to upper bound this by some absolute value, this absolute value inside the integral. Then we upper bound this by the absolute value of each of the terms in the summands. Now we can, well, we extend, because this is a non-negative function, we can extend this slightly to the integral from 1 to infinity. And how to compute this? Well, this is very simple. The first term, for instance, is, well, you can compute it explicitly in terms of the complementary error function, right? This is regarding the first term, the 1 times this. The second one is can be computed easily, but doing integration by parts, and the third term is integrating by parts 2 times. All in all, what you get is this expression, basically some rational functions multiplied by the complementary error function evaluated at square root n over 6. And in the second term is an exponential function to the power of minus n over 6. All in all, this can be easily upper bounded by some constant, absolute constant, 5 over 3 times exponential to the minus n over 6. And this is the first error term. Again, an exponentially, so this goes exponentially fast to 0 in the value of n, in the dimension n. Farewell. All in all, we are almost done. So what we did so far is the following. The sequence, we kind of approximated by the value ia of n plus the first error term. Then we consider in the integral the first terms of the Taylor expansion plus the remainder, arriving in this first part of the integral plus the second error term. Then we completed from 0 to infinity, and we had to subtract the integral from x of a to infinity. That was upper bounded by the third error term, E3 of n. All in all, it looks like this, what we did so far. So I of n can be written as these three terms of the asymptotic expansion plus some errors. Two of them are exponential errors, and the second one is, as I mentioned before, one which is kind of dealing with the size of this Taylor expansion so far, of this asymptotic expansion so far. Let me mention here that, of course, we could keep obtaining more and more terms of the asymptotic expansion. It's as simple as we did before. But this is enough for proving the monotonicity, because considering the difference of the sequences I evaluated at n plus 1 minus I of n, well, we lower bound the term evaluated at n plus 1 by the part where the main value of the integral is concentrated, evaluated at n plus 1. You see? This part evaluated at n plus 1. And the worst case possible for the lower bound is subtracting all the summation of the sum of all the error terms evaluated at n plus 1. And then the minus I of n, we write the main part evaluated at n, and then we subtract again all the error terms evaluated at n. Then rearranging terms, we see that the main part has this form, is a non-negative coefficient divided by a term of the size n squared. And then you see that the error terms are of this form: exponential errors, which they go to infinity to 0 much faster than the main term, and this error term, which is of degree 1 over n to the 5 over 2, which is larger than n squared. And this is why we took 3 terms, because when arriving here in this error term, this is very easily computed, an explicit error, an explicit n0, so that if n is larger than this n0, then this is always non-negative. Or in other words, this is always winning against these 2 terms. Okay, so this is the main idea of the proof. Of course, you see here a coefficient, a capital R, which is not explicit yet. Is there some question so far? I think it was more or less clear, right? Okay, if not, then I go on. Of course now, and let me say we were stuck up to this moment, we had this result already done for 3 or 4 months, 3 months, I think. We were struggling to prove computing explicitly the R, but it is very troublesome, very technical also. Then we had to contact some expert on numerical analysis. We contact then Ferenc Barza. He's a postdoc in Szeged, and then he very nicely explained us how to do this. So it's very technical. I won't explain everything, but let me first mention a couple of things before mentioning how to compute this R explicitly. So doing the same ideas than here with the same computations, one can also compute the concavity of the sequence. In other words, so the concavity would say that I of n plus 1 is greater or equal than I of n plus 2 divided by 2. So you consider twice this term minus the other 2 terms, and you aim to show that this is non-negative for some large enough n. If you do so with exactly the same computations we did before, you would arrive in a non-negative coefficient divided by n to the 3rd degree, and those error terms with different coefficients that I'm not even writing, and the problem is that the second term would be still the same we wrote, of the same order than we wrote before. Of course, that's then not enough in order to show that this is concave, because here you would have a 1 over n to the 5 over 2, which is smaller than 3. And so this is smaller than this term. This is just showing that if you have to do the same with a fourth term, So if you do so, then you arrive in here the same size, but here then you would arrive in an error term of the form 1/n to the 7/2, and that would be sufficient to show the concavity as well. A bit more technical, but that's it. Now we go into the upper bound, and I'm near the end of the talk. So the idea to show this, to show the upper bound, the capital R, I will mention in a second. But before, let me say what's the value and what's the result. So the seventh derivative can be proven that in this interval is upper bounded by this 0.79461, whatever, some constant. And then with this constant, one can check that this condition is fulfilled when n is greater or equal 76. And so in order to prove that this is also true for every n greater or equal 3, you just compute it explicitly with the closed formula, with the exact formula. And that's it. So this is the idea of the whole proof. And finally, let me mention that how to compute the R. It's very lengthy, but well, it was basically using ideas from interval arithmetic, automatic differentiation, and some particular ideas of analytical methods. The idea was basically you want to upper bound some derivative of a function, and then what you do is step by step. What you do is you compute the Taylor expansion, the coefficients of the Taylor expansion of a function. And of course, our function is very difficult. Our function, the x of t, was square root of -6 logarithm of sine of t over t. This is very hard. But then you have to look at this function as a composition of simpler functions. A bunch of compositions of very much simpler. And then once you do that, then you keep computing one by one the coefficient terms of up to the certain degree you are interested in for the simpler function. And you can actually compute not just the coefficient, but upper and lower bounds for such coefficients. And then what you do is using the ideas of Fadi-Bruno again on the Taylor expansion, the coefficients of the Taylor expansion of composition of functions. And you can do this step by step, computing upper and lower bounds for each of those coefficients until arriving in the corresponding to the seventh derivative of the of x of t. Then you are not yet done, because you have to prove it for the inverse function t of x. But again, you use the ideas of Fadi-Bruno, and you compute the coefficients of the Taylor expansion of the inverse in terms of the coefficients of the original function. And you upper bound and lower bound one by one until the end. So this is more or less the idea, how to show it. Okay, so this is the main references of the talk. That's pretty much it. So thank you very much.
Thank you very much for this talk. So any questions for the speaker?
Yes, thanks.
I have a question. First, thanks for the nice talk. You mentioned at the beginning that your sequence I of n was extended to the real numbers when you had this red graph.
Yes.
Right? But how do you do that? Because you raise a negative number to a power there, because you have sine t over t, and then you have to the n. How do you extend this to the real numbers actually?
I mean, I don't know exactly. I think they used. I don't know exactly, because this is not what we work on. But I think they use somehow there is. I had the feeling when opening the paper and having a look at it that they had a canonical way to do that. So I don't know how exactly, but they had a canonical way to extend this analytically. Maybe using some. I think they call them Bessel functions, I think, but I'm not sure. I can't tell so far. I'm not sure. I can't answer to you properly.
Okay.
But I think there is a canonical way to do that. It's not that hard, I think.
Yeah, I was just looking at the formula. It doesn't seem that you can just plug in real numbers there, right? Because you have this negative.
No. It's much more lengthier than just saying I replace n by rows. No, it's not like that. It's not like that.
Right.
How was it? I mean, we could open the paper.
Oh no, I can have a look later. It's no problem. I was just wondering if there was an easy way to see that.
But I think it's somehow canonical, somehow how to extend that.
Okay, thank you.
Yeah, you're welcome.
So any more questions? So perhaps I'll ask a quick one again. So in your first asymptotic expansion, you had an error which was of order 1 over n cube, big O of 1 over n cube.
In which, where?
Here, yeah, in the asymptotic expansion, yeah.
Ah, sorry.
And in your proof, you had something like, so n power minus 3, and you had something like n power minus 5 over 2. Does that give you a worse error term, or? Or you have to do one more step, or?
So, but do you mean for, what do you mean for?
For the big O, you see.
For the, no, for the big O, you need another term.
Okay.
Yes, you need another one. But we stopped there because it was already enough. But yeah, for the...
That gives you the coefficient, but somehow the argument that you gave, it seems to me that it gives a slightly worse error term, right?
Yes, exactly. We are losing quite a bit there.
Okay, yeah.
We're losing quite a bit, but still, so that we really focus on what was needed, so to say.
Okay.
But somehow the idea is kind of simple, to compute more and more terms.
Can I just ask a question about the original geometric definition? You showed the section of the cube in 3 dimensions. There you are. Yes. So that is it or is it not the same as the projection onto a hyperplane of the whole cube in that direction?
I'd say no.
So it's very important then that you are taking the intersection of the hypercube with the hyperplane which goes through its center rather than any other point.
Exactly.
Yeah, okay, thanks.
Exactly, yes, sorry. It's through the origin, yes.
Yes.
I mentioned in the, so when I mentioned this, I really meant sections through the origin.
Yes, but the projection onto the hyperplane of the whole thing, that must be the same shape, but just slightly scaled, is that right?
You mean exactly the same shape, but
a multiple of it. Conjecture.
In this case, yes. But I'd say in general, I'm not sure, because the number of faces of such an intersection is always at most, it has 2 and many facets, but the projection might have, well, I'm not sure, but the number of vertices in the cube is exponential. Maybe in larger dimensions.
Yes. But
it's much more roundish, the projection, than the section, I'd say. It's much more roundish. Like it looks more like a circle, I'd say, in high dimension, but.
Intuition tells me that they're the same and have 2n corners, but
yeah,
I'll have to think about it.
Okay.
Thank you.
Thanks. More questions? If not, let's thank the speaker again for the very nice talk.
Thank you.